Welcome you all to the class number 19. And today is the 23rd of March 2020. You are with me in finite element methods. So last time we developed the idea that first of all we have the solution, we have the displacement solution obtained from the inversion of the matrix, the K matrix inverse times the externally applied force, and we get the response, which is the displacement response to a given kind of load. And then from that displacement, I talked in the class already that it is not that useful because for the design point of view, especially for the case where you need the finite element, you will need to know the magnitude of stress or strain. It is unlike the 1D element that we know very well about them. 1D element, you might need the axial force. Actually, that is also a kind of stress. If you just calculate a little further, then you just convert from axial force to stress or shear force or the bending moment. Alright, but now we are looking into the continuum. We are looking into the domain, which is the 2D or 3D. So we will look up for the stress magnitude, and the stress magnitude should not exceed the capacity of the material. That's all about the design. So we convert from the displacement solution to the stress or strain using the B matrix. We will actually just obtain the displacement from the step before, and then we look into this information element by element. So I'm gonna go up, look up for the displacement that are relevant to a single element. Alright, the operation that we are going to do in the programming is going to be the element-wise operation. That means if I look up into element number 15, I'm going to look up for the relevant nodes and displacement for those nodes. I take this information in and I put this displacement vector for an element multiplied by the B matrix. I end up with a strain. I have a strain. I multiply strain to the D matrix. I get stress. Alright, and then I get stress. I store the information in the ISTS, or for a strain ISTN. That's going to be the three-dimensional matrix. We store it up, but when we want to display or visualize the information in a graphical format, of course you will not want to look up into the ISTS or ISTN, which is a bunch of numbers and it is very difficult to interpret. You want to visualize the data in a form that is very friendly for you to understand. So this visualization will be in a color plot visualization. And then how to plot it out? The thing is that all stresses and strain are associated with just the integration points. That means if we want to plot, we have to do the extrapolation, because integration point is not all the way up to the boundary of the element. So we got to extrapolate to the side of the element. The point is that after doing that extrapolation, we will find that stress is not smooth. It is not smooth because it is according to the scheme of finite element. We ensure the continuity of displacement from the scheme, right? We have the displacement which are continuous over the boundary of the domain. That's the way we construct the shape function to approximate the displacement. But we didn't ensure the continuity of the stress and strain. It is the derivative of the displacement, so we are not saying anything about the continuity of such. Then, the problem arises when you want to plot out or visualize the stress or strain, because now it is not continuous, and it is sort of not making any sense to see this how to say, what is opposite to continuous, discontinuous or discontinuity of the stress and strain over the boundary, because in reality the governing equation is not simplified using the shape function which are easy for us to use. You understand that, right? Because the exact solution that many times that we cannot come up with actually is like a very complicated solution. So the displacement is satisfied, the continuity of displacement is satisfied, and the continuity of the derivative of displacement, that means the stress and strain, are also continuous over the boundary. So we conduct the stress smoothing using the least square technique. So we know that when we construct the profile of stress and strain over the entire domain, we do it element by element, and then it is like the tiling, right? So you might have the discontinuous field values over the boundary, and then we try to smooth it up by giving a continuous function of stress, and that use the concept of finite element again. So we say that instead of constructing the distribution function of stress using the integration point values, we will convert from those integration point value to the nodal point values. That's what we derived in the last time, in the last lecture. So doing that, then you'll be getting the nodal point stress and strain. Okay, so we'll be able to plot it out. Once we plot it out, as the distribution function is constructed at the nodal point, then you will not have the issue about the discontinuity over the boundary. Okay, so today we are going to implement those concepts in this code. All right. Basically, the part here for input, I intend to make some change. So we are going to use the input file after this, but I think I'm not going to do it in the regular class time. So once I have a good mood, I'm gonna live again and give you the procedures that I convert this part into the input and output from the file. So later, all right. But we will now emphasizing on the F6 like this. I think I'm gonna have to change it as well, because later on the assignment of the externally applied force will be carried out in a more systematic way. This is just a problem specific coding just to illustrate the problem. So I just do it in a sloppy way like this, but we're gonna try to make this code more and more systematic and more generalized. Okay, boundary condition like this enforcement. Okay, this is going to work. We get the displacement. What is that? Zeros. Okay, why did I comment that out? Don't remember. Okay, we have the deformed shape plots over here. I'm gonna make to just at least make it easy for us to detect very quickly where exaggeration factors given here. Okay, and that's it. So we can do the stress recovery routine somewhere around, this is what, displacement equals to blah blah blah. Okay, and okay, at this point we insert, okay, I know that this is from the penalty method. Alright, we do the insertion of boundary of restraint. Let's say restraint, ESTRAIN, restrained, DOF. Okay, back into DISP. The reason is because as we did the row and column elimination, those entries are removed in from the DISP, right? Because we remove row and column, so we need to insert them back, because that mess up our NDE or those degree of freedom setup we had initially, right? So we insert back, then the DOF in the DISP will be all contained. Okay, so that means this location here should be a good point where we conduct the stress recovery. Okay, so I come down here, copy and paste, and this is the stress, well, basically it should be strain and stress recovery routine. Okay, so it is sort of like a subroutine, and it's gonna be long because, you know, if you want to come up with the B matrix, that means a lot of work has to be done over here. Okay, alright, give it plenty space in order to, well, play around. So this is our playground, and we need the displacement to stuff into the little element displacement vector, and that depends. Okay, so basically, first of all, we're gonna need the for, right? For I equals to 1 to NELE, because this is going to be the operation, element-wise operation. Element-wise operations, we're gonna start from the first to the last element. In order to what? We want the ISTN, and we also want ISTS, and these two will be assigned. So zeros, how many? We have first index, NELE, right? First index means the element number, so it's gonna be NELE. The second index, we are talking about the integration point. Integration point, the number of integration point we have in total is NINT, right? And the third one is the component of stress and strain. So this is going to be 3. That's it. Close. Likewise, for the stress, we also have 3 components, so that means we assign the same size. And for the ISTN, I will do IJK. Alright. The I and J, okay, it is easy to understand, but the K equals to 1, that means strain XX. K equals to 2, it means the strain YY, and K equals to 3 means the strain, the gamma. Okay, I'll just do it XY like this. Likewise, that's gonna work in the same way, identical way with the stress. So XX, YY, and XY. Okay. Now we have initialized the protocol for understanding the storage of the stress and the strain information. Now we're gonna start doing the code for here. So I start with I equals to 1 to NELE. So that means in this very element we are going to operate or do something for an individual element. First of all, I think we need the EDIS. EDIS is the element displacement. For example, if we have a Q4 element, we're gonna need 8 displacements, right? Q8 we're gonna need 16, Q9 we're gonna need 18 displacements. Now that depends on the shape function that you use or the element type. So it is the zeros. The displacement vector here should be 2 times E type by 1. It is just the vector. So the vector contains 2 times number of nodes for that element, and number of nodes is given by the E tip, right? Comma 1. We initialize this and then we will fill it up. We will transfer the information from DISP to EDIS. So we're gonna have another for loop for J equals to 1 to E type. So in this for loop here, the operation will be like we go look up for information from DISP and then pull that information down to the EDIS. Alright, the EDIS comma, you're gonna have a headed index over here. Well, it is not that headed anyway, so it is 2 times the J minus 1. Another one is going to be the 2 times J. Right? I think you can imagine with me. If you cannot, watch this again. Sorry, we are not in a real classroom, but I think you guys can try. So we're gonna talk from the first node, right, to the 8th node, 9th node, or a 4th node. So in each node, you're gonna have 2 degrees of freedom, right? This is just number of nodes, but the EDIS has the dimension in row direction being 2 times of number of nodes, or that is the number of degree of freedom. So the operation in here is the node-wise operation. Then you're gonna have 2 things going on within one cycle of this operation. Alright, so 2J minus 1, for example, if you look at the node number 3, you have degree of freedom 5 and 6. So 3 to 2 you get 6 minus 1, you get 5, and this line you're gonna deal with the degree of freedom number 6. Okay, just that. DISP, of course, and then we're gonna look up for the index for DISP. Of course, DISP will be comma 1. Okay, that's the simplest thing to do. Right. So, which point or which entry in DISP that we are going to look up for? That is coming from NNDE. Okay, the nodal point mapping. I use Nmap or NNDE. NNDE is a number of node, right? Nmap. Okay. Nmap. The first index for Nmap, we will talk about the element number. So the element number is stem from the I value. The I is here. So the element number is stuffed in, and then the second thing is gonna be the node number. So it's J. Okay. So node number now. Node number means 1, 2, 3, 4 until the last node of that element. Okay, this is the J. But then the Nmap will give you the node number according to the global node numbering. So it could be node number 156. Your node number 3 in this given element could be the 136 or some number. All right, but here we pull it up from Nmap that we construct before. All right, so we get the node number. We get the node number, but that's not what we want. We want the degree of freedom number. Lucky that we set up the degree of freedom and node numbering in a ties up manner. So we tie them up using the 2 multiplied by the node number minus 1, just like before, right? And there you go. Guys, if you are watching and if you find that the sound or something is not going well, it's not clear, or whatever problem, then let me know. All right, or if you really cannot understand something, please let me know. I will check at your comment, so at least I have some idea. It is not that interactive, but well, at least I can come back to your comment, which is about 10 seconds behind. Alright, so let me come back. I will fill this up. So the second degree of freedom, well, basically this degree of freedom means the X displacement, right? And the second one is the Y displacement. There you go, N4. Sound is clear today. Okay, great. Yeah, last time I think the air purifier or some setting in the program is not working in the right way. So we heard some sort of like the jet engine sound in my room. But to be frank, I didn't live from the airport or from the hangar or somewhere near to the aircraft. Okay, so that's some artificial sound. Okay, now we migrate the information from this into EDIS. We have the displacement associated with a particular element that we are working on right now. The next step, we are going to copy from above. From above. Why do we need to do that? Because we want to find out the B matrix. So I think we're gonna need the element XY like this. Okay, let me just copy down the whole thing. All right, the operation that we need will be just up to here. We did the numerical integration previously, but we do not have to. We want to find stress or strain at the integration points, and we will not sum them up. We are not looking up or finding the stiffness matrix. So let me copy, and then I'm gonna just streamline the code. So the thing over here is pretty much like this point here. Okay, we just copy the element x, y coordinates to here. Okay, and you see we have the for loop from J to element type just like before. We're gonna migrate information from the xy core to the element xy coordinate. So we can group all of these activities up into just one for loop. So the code looks neat. Alright. And okay, this is unused. Over here we loop over the Gauss point. Loop over Gauss point, we have that many NINT. Oh, well. Alright, over here we can, how many Gauss point do we have? NINT square, sorry. So we just need to add this up. Alright, yeah. So for J equals to 1 to NINT, and for K equals to 1 to NINT. Right. Actually I do not have to do all of that. I can just copy this thing, loop over Gauss point. Okay, I just keep this thing there. Clean this up, delete. Okay. What I just did. Okay. So we go up and find the C and eta values, and we have the code. Actually, I should do the save as. Alright. Save, where is it? Save file as. Okay, main. Okay, UPD. Okay, main update one. UPD. Oh no. Okay, there you go. Alright, get the C coordinate, get the eta coordinate. And then we find DC, the shape function the global coordinate, Jacobian of Transformation. We find all of these using the eval subroutine in the separate file, and then we find the B matrix. Okay, the B matrix was first initialized this way, and as it is initialized, we fill up the entries in B matrix accordingly. So the B matrix, the operation is repeating for e tip times, right? Go back and look up into your notes. So we have the similar operations going on for these many times, which is equal to the number of nodes. So basically, we the first line, the B mat, this one here is for the calculation of the strain epsilon x. This one is for the epsilon y, and the third one is actually for the gamma xy. Right. So JMMA xy. I will note it down like this so you understand better. This is what? Epsilon x, epsilon y, and this is epsilon x. Okay. Alright. Now we get the complete B matrix. So the B matrix along with the displacement, element displacement, we are going to get the strain first, right? So let me assign the strain. ESTN, element strain, is equals to zeros. how many? We gonna have 3 by 1. This is the dimension of the strain vector. So ESTN actually will be equal to the B matrix multiplied by the EDIS, element displacement. That's it. Very simple. We get ESTN. We will later migrate this ESTN into the ISTN that combines all integration point strain in the very same tensor. Okay. Well, later on we will need the ESTS. So ESTS actually is the same. I just want to just make sure that the dimension of the stress and strain will be in line. And ESTS is the strain and the rigidity matrix, right? The rigidity matrix, what is it? Let me check up. Rigidity matrix is given here by the DMAT. Okay, so I take the DMAT. For here, my code here is not accommodating more than one element. We can extend our code in order to do that. For example, if we want to do just some silly analysis of the elastic behavior of the, let's say, planar RC, alright? Some very, very simple thing like that, where we know that RC is going to be non-linear, but we can do more than one material. Let's say some simple more than one material analysis. Then DMAT will be stem from the matrix. But right now, that is just the administrative issue to cope with, so it is too easy, and then we might just do it separately out of the class time. So DMAT, alright, it could be DMAT and with some sort of index in there in order to pull it up from more than one material, alright. DMAT multiplied by ESTN, okay. So this is again for just elastic, material IAL. If you are doing inelasticity, over here it will not be as simple as the linear function like this. So over here at this point, it is going to be sent to a separate subroutine that takes care of the inelasticity. So for the inelasticity or nonlinear analysis, you give the strain as the input. One strain is given into that subroutine. That subroutine will figure out the plastic strain or whatsoever index or parameter used to identify the level of inelasticity, which is going to be a big issue after this. We are right now not focusing on this point. We are focusing on the overall big body of FEM. But I just give you the idea that this point here for the inelastic material will not be as simple as this one. But the features or the how it works, it is just obtain your strain, give it into the nonlinear rules for each material, for the each inelastic material you deal with. No matter what kind of plasticity theory you are dealing with, it is working this way. And then that subroutine might be developed by somebody else, might be from your professor, from whoever, okay? And then that subroutine will be giving you the stress. So stress will be the output, but the output, it is not coming from the linear relationship like this. Okay, but okay, for our purpose, we already obtain what we need, N4 and N4. Okay, well, don't forget that once we obtain this information, we need to store this information into our ISTS and ISTN. Okay, so I gonna give you some sort of dummy. dMmy equals to 1. Okay, so we will just stuff everything in ISTN. What is the index? First index indicates the element number, so it's gonna be the I index. The second index is the integration point number, so that is the MMY, right? So operation is within the element. We hit this point here and we enter into the first integration point. We finish this loop, we come out to here. No, we're not coming out to here, but we finish this loop. dMmy is going to be dMmy plus 1. So we come to the next integration point. So this gonna repeat for NINT square time, and then you're gonna get the dummy index, okay, updated every time you go through this loop. Okay, and the last one is going to be this colon, because we will transfer the information from ESTN this comma 1. Okay, all right. So strain epsilon xx, epsilon yy, and gamma xy, all three will be transferred into this ISTN, whereas the I stands for the element number, the dummy stands for the integration points that we are working with, and the last one, okay, the component of the stress of the strain. I just gonna repeat this one, copy it and paste it again, and it will be stress. Alright, so we have stresses and we have strain. Basically, for this one, if I do not want to have too much information in my computer, I can just comment this out, because I know that strain and stress right now, they are the linear relationship, right? So they are holding the linear relationship, so I actually do not have to store this value for stress. I actually do not have to compute this. I can know this later. But, well, it's up to you, or it's up to the resource. If we can handle, we can keep all of them, then we just keep all of them, right? Just take some of your storage, but you know, the problem we are dealing with here is just a simple, very small problem in comparison with the actual finite element problem that's gonna make you money when you work or when you practice. That's gonna take a whole bunch more degree of freedom and data. Right. So right now we have everything stored into ISTS, ISTN. We can close down this N4. Okay. That's it. We get stress and strain at integration point from here. Very simple. And this is just a stress recovery routine. So next step is to smooth up your stress in your domain for the visualization. So stress and strain least square smoothing, LEASTQUARESMOOTHING, least square smoothing. We're gonna see what we're gonna end up with today for the bug. I don't feel that it's gonna bug, but okay, who knows? Bug always strike. So Now let's look into the node we had from the last time that we developed. I will also need to look at that too. So in the class number 18, the previous class. Okay. Right, the last page, you see that we have the operation that looks pretty much like the standard finite element operation. So we going to have the operation in the element-wise operation first. For I equals to 1 to NELE. Okay. Element-wise operation, but over here I think we have something additional from what we have as a resource that we have currently. Look at this. It's too bad I cannot bring up my iPad together in the same page. Well, but I just expect that you have the notes ready for you handy. Did I upload the notes last class? If I didn't, then I will do it today. Okay, but we have left hand side and right hand side. One side that looks like the force vector and another side looks like the stiffness matrix. So I will just assign, okay, the F, what I used previously, F, okay, F sys and K sys. Okay, so I use the same variable name like before, and K sys. F sys gonna be zeros, how many? 2 times NNDE, comma 1, and the other thing is the K sys. It is not actually stiffness matrix, and it is not actually the force vector, but the shape just look alike. So I just name it this way. And last class I named it like this, so it is consistent and it might be easier for you to look into this matter. Alright, now let's look at the big picture bird's eye view first. We are going to construct the I'll call it force vector and stiffness matrix now. Okay, so we are gonna construct all force vector and stiffness matrix, and we are going to use the concept of numerical integration. We will conduct this operation at the Gauss point. Alright, so inside you are going to have the 4j equals to 1 to NINT, and for k equals to 1 to NINT, and then I have the N4. Okay, alright. For the, I will type it here. For the F, it is equal to sigma sigma twice. So we have the summation in the integration point of phi transpose, which is the shape function vector evaluated at C and eta, okay, multiply by the sigma stress. Basically it is the stress at integration point or strain at integration point times the Jacobian of transformation times the weight in J and times the weight in K. Okay. This is the F. And for the K, if you don't have your notes handy, okay, so we're gonna have to summation because we conduct the numerical integration into dimensions, and then we have the phi transpose times the phi. Okay, that means clearly we have to construct the shape function vector. Jacobian of transformation is actually the product we have W and W, and then multiplied by unknown, which is the stress and strain at the nodal point. Okay, pretty much like this. So let's just look at what we want strategically, right? We always get scared of this thing. Look at it strategically. Phi. In order to find phi, you just need to open your node for the shape function and for the different elements. This is easy. We stuff in the C and eta values. Terribly easy. Stress we have from ISTN or ISTS. Okay, that depends on which one we want to smooth up. And Jacobian of transformation. Well, this is a tricky thing because in order to get the Jacobian of transformation, you cannot avoid the calculation of derivative of shape function with respect to C to the local coordinate and the derivative function of the global coordinate to the local coordinate. Those kind of things needs to be carried out. Alright, the weight is easy. We have all the weight listed off already. Alright, okay. Now you know that if we need Jacobian transformation, we are going to use this thing, this subroutine eval. In order to use eval, you need to get all of these. So I just copy. Okay. Here for sure. Again, we come back and find this. Let me see. Actually, can we combine this code together with this one? We get the integration point, stress, strain, and then we can also use the Jacobian information. Well, actually, yeah, we can. Okay. So we don't waste the line, we don't waste the time as well. Okay, so this operation does not need to be repeated down here, but then I will just cut this and put them in here. I'll be saying that it is not only the stress recovery, but it's also the stress and strain, the least square smoothing there. Okay. So we do not need things in here. Okay, up to and I know. Oh, okay. Delete and up. Now, what do we need to do? We need let's see, the eval. The eval works and we don't want to touch it anymore. I think I'm gonna need to come up with a new function. Let's say if you can see here, function NSHP. Okay. And okay, I call the vector of shape function by the name NSHP. QSHP. Okay. Quadrilateral shape function. Okay. Well, let me see in here. Yeah, we're gonna need C, we're gonna need eta, we're gonna need element type. We don't need E, X, Y, Z. Okay. So we're gonna have if E type is equal to 4, then we list out the shape function for Q4. Else, if E type is equal to 8, then we list out, and else if element type is equal to 9, then we list everything's out. And if, okay, so in there, first of all, n shape has to be allocated to be zeros. E type comma 1, that's copy this. And then n shape comma equals to then home it will be comma 1 only. Okay, 1 2 3 4. Okay, and 5 6 7 8. And copy everything down here. 9. That's it. Okay. And well, just fill the things in. So go back, look at the shape functions. Oops. Let me check finite element and the shape function for Q element. This is the chance that we make use of the shape function, not the derivative of shape functions, right? Previously, we never used shape function in the calculation. Well, you can say that, okay, we cannot come up with the derivative of shape function using the shape function. Of course, yes, that's correct. But the point is that we never really have to write down the shape function into the code because we don't use all of these in the calculation, but we use it for the post-processing over here. So, right, let's start. 0.25 multiply by something. Okay, 1 and C times 1 and eta. I just leave it this way so I can just put in the sign later. So the first one, 1 minus C and 1 minus eta. The second one, 1 plus C and 1 minus eta. The third one, plus and plus. And the fourth one, 1 minus and 1 plus eta. Okay, it's all done. Let's come to the Q8. Okay, Q9 is crazy. Okay, I just passed the Q9. Do it Q9. Alright. 0.25 times c square. So c times c, and it's gonna be doing something with another c, so I put it this way and then multiply by eta square eta. And I'm gonna drop the sign in soon. Just remember that last time for the Q8 we did something wrong with the sign, but that's the derivative of shape function, right? Okay, we will make sure that the shape function itself has nothing wrong for the 8. Okay, so I just remind myself minus and minus. Okay, I'm gonna look up where it's gonna be minus, all minus here, and the third one is plus, the last one minus and plus. Okay, so the remaining are plus, right, and plus, and plus, and the last plus. Alright, okay, c square minus c square plus c square plus c square minus eta square minus eta square minus eta square plus. Alright, great, looks good. And number 5 and number 6, 5 and 7 are pretty much the same. 0.5 times, what is that? 1 and c square multiply by eta square and eta. Copy and paste. So number 5, well, minus. Number 7 is also minus. And eta square minus eta square is going to be plus. Okay. Well, over around here is the place where we have very high risk, because I myself can always leave some bugs in around here. Too many things, too many equations, expression. Okay, 7 square and then eta square. Alright, how about number 6? Number 6 is 0.5 multiply by c square and c times what? 1 minus eta square times eta. Okay, copy and paste on the number 8, pretty much alike. Number 6, c square plus c, and then 1 minus eta square. For number 8, c square minus c and 1 minus eta square. There it is. The last one, 1 minus c square times 1 minus eta square. That's it. Okay. So Q9 done. Now we move back to Q8. Q8. Where is it? Okay, got it. Find it. I think I should look at the one here. Okay. for Q8. It is long. Minus 0.25 C minus 1 eta minus 1 and 1 plus C plus eta. Okay. Okay. The second one, minus and 1 plus C. 1 minus, oh no, 1 minus eta. Oh, come on. Okay, I just hate it. 1 minus eta, eta minus 1. We should just have the Okay. I don't want to do anything with it. 1 plus C, 1 minus eta is identical to eta minus 1 and clear that out, and then 1 minus C plus eta. Okay. Well, be patient with me a little bit. Okay. This procedure is just boring, I know, but okay, let's just fix this in. So I have the minus sign in front of a quarter, C plus 1, eta plus 1, and 1 minus C minus eta. Oh, right. Okay, next one, a quarter without the minus sign. C minus 1, eta plus 1, and 1 plus C minus eta. Eta minus 1, C minus 1, eta plus 1, and 1 plus C minus eta. Okay. 0.5 times 1 minus C times 1 plus C, 1 plus C, and times 1 minus eta. The next line. Okay, I just retype. Copy is 1 plus C, 1, what is this, number 6, right? 1 plus C, 1 minus eta, and 1 plus eta. 0.5 times 1 minus C. Where is X? I cannot find X. 1 plus C and times 1 plus eta. Right, 0.5, 1 minus C, 1 plus C, 1 plus eta. Last one. 0.5 times 1 minus C. No. 1 minus eta. And 1 plus eta. Okay. 1 minus 1 plus. Okay, alright. We have Q elements, shape functions listed out in here. Save it. Oh, I never saved this before. So Q SHP will be the name. There it is. So we come back to here, to the main. Here let me see. We need to evaluate the Q shape, the N shape in here, right? So I just do it here. Okay. I execute this subroutine Q shape. Oh, need this. I execute it. I get N shape. The N shape okay. The N shape is available. Now we want to conduct the numerical integration. So this part here, let me see. We need to stuff all of them into the right place in the system matrix. So we're gonna have the plugging in subroutine. Okay, fine. Let's just look at the big picture first. Okay, so of course the F will be computed in here, the element 1 and the K. One second. So basically we're gonna recompute the F and the K, the element F and the element K. So we need to initialize the value. FELE equals to zeros. It has to be every time, right? Because we will do numerical integration, so we'll just initialize it. FELE equals to, oh no, wait. It should be outside. KELE is equal to zeros. How many? E type comma 1 and E type comma E type. Well, the size of this element force and element stiffness will be just half of the actual one before. The actual one, the size of them, right, are twice as big, so E 2 times. That's the number of degree of freedom. But over here, as we conduct the calculation, it will be separate calculation. So the stress will be carried out for one component at a time. So the FELE and KELE, okay, they are just assigned this way. We assign them out here before we come into the numerical integration loop, because we're gonna sum them up all the way up to the end, and then we will stuff them into the Ksys and Fsys. Once we stuff them into the system matrix or system vector, then we repeat to the next element. We need to reset to 0 because the nature of the operation in here is going to accumulate the values for FELE and KELE, right? So we have Jacobian transformation, we have everything. Now we need to compute FELE. FELE, sigma and sigma is from 4 and 4, okay? But it will be sigma by FELE plus, okay? We need to accumulate. So we have this sigma and nested sigma. Phi evaluated at C and eta. The phi evaluated at C and eta come from N shape. And multiply by whichever stress or strain you want. Okay. Basically, then we do not need to store this information. Okay. I used to just keep this information and then do the separate smoothing outside, but now we might not have to. Sometimes you might need to keep the stress and integration points in order to track the inelasticity, but now it is not necessary because we will later on obtain the nodal point stress and strain. So then I just can clean all of this up. Okay, just comment now first. Maybe comment. Okay. N shape multiply by stress or strain. So whichever component we want. Okay. We have in total 6 components. Which one? Let me think a little bit. I am thinking about the strategy to I make it this way. So make them all 6. And 2 and 3, 4, 5, 6. This first one. Well, the thing is that the K matrix is going to be the same, so you don't need to make many of them. But the F will be different due to the different magnitude of different component. Strain XX, strain YY, gamma XY, sigma XX, sigma XX, sigma YY, and tau XY, epsilon. Epsilon XX, epsilon YY. Okay, now we have all notations. F Eli equals to times, for epsilon XX it will be ESTN. Actually these two we can just comment them out. Okay, they will be controlled by these two, of course. E strain 1 times what, Jacobian of Transformation times the weight. When we look up WG, yep, let's just copy it then. Okay, beautiful. Copy this. And change the variable names. We have some other things to change as well. Let me do it this way. Delete. Four, 5, and 6. And this is STS. No. Okay. 3, 2, 1. 3, 2, 1. Okay. No, 2. Okay. 1, 2, 3. 1, 2, 3. Stress and strain, Jacobian transformation weight. This looks stupid. This looks really stupid. Let me make it more novel. No. Let's just keep it this way. Don't. Not a good idea. You're gonna end up with trouble. KELE is equals to KELE itself. So, what is the expression for KELE? Okay. So, it is the N shape. Oh, that means in the previous class the N shape is the it's a row vector. Okay, I made it the column vector already. So okay, so N shape times N shape transpose. Okay, and Jacobian of transformation, and what else? And the weight. That's it. Oops. I have double weight. Okay. I'll read your. Okay. We have some comments. Line 15 shouldn't be transposed N shape. Line 15. Where is the line 15? When line 15 for the Q shape, or what? Which one? Line 15. Oh, line 153. Line 153. Okay. Line 157. ESTS21. Alright. Okay. That's it. Thank you, Milk. Okay. First, okay. 157 corrected. Line 153. Shouldn't it be transposed 153? Shouldn't it be transposed of N shape? Well, the N shape last time in the derivation. If you look back into the notes in the derivation, that one I made that N shape in row. Okay, it was the row vector. But over here, when I made in the routine the Q shape, right? What you have from N shape is the column vector. So as you have the column vector, it is the same as the transpose of phi in the derivation. So the dimension is consistent. Alright. Let me see. Someone call, but I will not pick up. Okay. Who called my landline phone? Okay. Is that all good right now? I think it is all okay right now. Let me know if you still see something that does not look okay to your eyes. KELE is the accumulation of KELE with the phi transpose in the nodes times the phi vector. Okay, so we have things switch around a little bit. And then Jacobian of transformation. Okay, Navinda, thanks. And weight. So that's all. After that, the dummy, okay, will be there. The N4. Okay. And then out there, once we finish up these accumulations or the integration or numerical integration, Gauss, I will call this point the numerical integration. these two guys should be executed. Okay, numerical integration. We are done with numerical integration. Now we will need to plug in the entries into the system matrix. Okay, in order to do that, you're gonna have the for loop again. Note down PLU plugging in element vectors or matrices. Let's just one. We do it one at a time, right? Vector and matrix into sys. Sys means the system vectors and system matrix. So we have 4 j equals to 1 to e type. Okay, this is gonna be 1, 2 element type again. This is actually identical to what we had here, right? Then the operation we had here, we had 4 because since we have 2 degree of freedom at each node, then you have two operations in one direction and 2 operations in another direction. Then we have 2 squares, so it turns out to be 4. But over here, since we are doing it just one at a time, so we have just one unknown stress in one system of equation. So we will have the K sys. This is going to be brutal again, K sys plus the KELE. Okay, right? So what is the index for K sys and what is the index for KELE? The index for KELE is going to be easy, so it's going to be J and K. That's it. So for a K sys, we need to plug this into the right place. So it is the n map I comma something comma n map, actually I comma K and I comma J. Okay, n map I comma J, n map I comma K. So I copy this. It is much easier than before because here we have m map multiplied by 2 minus 1 because we account for the degree of freedom. But this one, as it just comes up alone, so it's gonna be just as simple as this one. Where is that? Okay, I just don't like it that way. And then N4, wow, I indent the code. Just, okay, that's it. In the same loop, we can do the accumulation of the FEM. Okay, and it looks like we're gonna have to set it up. The FEM, yeah, it's too bad. Oops, sorry. Number 3, 4, 5, 5 and 6. Again, first one epsilon xx, second one yy. Just make sure that we come back, look at it another time in the future, and hopefully we can understand it. Or if I cannot understand it, I will rewrite the new code, which is my preference. Okay, so we have 6 F sys 1 n map, alright, I comma j equals to F sys 1 itself, because we need to top up the values, and comma 1D, okay, plus FELE 1, okay. If this one equals to the this1 itself, add up with FELE 1 and FELE 1. It's gotta be the J, comma 1. That's it. And there it is for 6 times. Delete. Wow. Now a lot of people are learning finite element from the audience list. I can see. Okay, 2, 3, 4, 5, 6. The shape of our F6 of the FELE. FELE has the dimension in row dimension. It has E-type rows and just one column. E-type rows and just one column. So each row will be plugged into the right degree of freedom, to the right node number, let's say. Now we are not talking about the degree of freedom. So it will be plugged into the right node number. So the node number come from the element number I, and this is the node number j of that element. So we get the global node number. The global node number is repeated over here, right? So if this one is equals to the f this one itself plus FELE 1 and 2, 3, 4, 5. This one is not. Is it FELE? Okay, it is FELE. Okay, 4, 5, 6. Okay, so this is the force vector is done. The stiffness matrix is done, and we have all stress smoothing done over here. Okay, let me save it. And now, as this part is done already, we have the smoothened stress. We come to here in order to present the data or to visualize the data in a graphical format. So the deformed shape plot over here, we have the first, this is the mesh plotting for the deformed mesh already. Alright, we will need to, should we plot in the same one? Sorry guys, I just move up and down. I'm making the decision. Mesh plotting, it should be the deformed mesh plotting. Okay, we have the exaggeration factor. So for I equals to 1 to NELE, for each element, then I will need to store the temporary x and y coordinates. So the temp x, tmxy, temporary x and y coordinates is equals to 0s, E type, comma 2. Actually, yeah, I make it temp 0, comma 3. So we will take the coordinate from for j equals to 1 to e type, we come here TMP what index j comma 1 is equal to MP j comma 2 is equals to okay, and temp j comma 3 again is equal to, so j comma 1 is equals to xy core of n map of element number I of the node number j, okay, comma 1, this is the x coordinate and then y coordinate we comma 2, and then the third one is the now it depends what we want to plot, so we have options. We have up here, actually we can solve first, right? So nodal point strain 1, nodal point strain 2, nodal point strain 3, nodal point stress 1, 2, 3. And 3. This is equal to inverse of the cases KINV equals to cases inverse. We inverse it this way and we get the KINV, so we do not have to inverse for too many times. And then if cis 1 so that's it. 2 3 4 5 no and 6. Okay, so our nodal point epsilon xx, actually I should copy paste epsilon yy gamma xy and sigma xx, sigma yy and tau xy. Okay, all figured out. So over here if okay PSXX PEXX plot condition, plotting condition PEXX equals to 1 over here, let me put it 0 for no plot and 1 for plot. So if you do not want to plot out the figure, then just set the 0. So for we're gonna have in total 6 figures, and sometimes you might not want to have all of them. PEYY equals to 1, gamma xy is equals to 1. So over here we have everything plotted, and what plot sigma xx equals to 1, plot sigma yy is equal to 1, and plot tau xy is equal to 1. So we're gonna have our plot out. Okay, and then I have all the if over here. So if PE xx is equal to 1, then it's gonna do this. And if it's gonna repeat, we cannot complete it in this class. Fine. Indent code. Okay. PE yy is equals to 1. Then the architecture is still not that beautiful, but I think I can come up with a more beautiful architecture later. Okay, and then plot sigma xx, plot sigma yy, okay, and plot tau xy. Okay. Right, the frame will be just like this, and then we're gonna have a plot for each individual. Once we have the temp in here, then we will execute the fill command within the if. Okay, the big picture is going to be like this. So fill will be executed within the if. So then if you don't set up the plot option to be 1, okay, which is over here, this is a place where you can set up the plot option. So if you don't want any of this, if you want to disable them, then you just zero them out. Okay, and then it will not plot that given stress component. In fact, if you want to get further information about principal stress, maximum principal, minimum principal, and maximum shear stress, you can also do the calculation around, once you get the nodal point values out, then you can find all of this. Data structure, in order to make the fill function work, you need at least 4 rows. At least 4 rows, what does that mean? It means that the polygon has to be closed. So we got to put the coordinate of the first node, second node, third node, and the fourth one turns out to be the coordinate of the first node. It repeats. Okay. So that's the thing. That's why it doesn't work, and it gives the error message, and basically it's nothing more than just this silly data structure incorrectness. So we look into here, I set up the data structure accordingly. So we have 4, and then the fill command just needs the first is the x coordinate, second is the y coordinate, and the third one the height, the magnitude, intensity of that point. So let's execute this function. So it is like a try fill. Okay. Alright, so I just set 2 figures, just play around a little bit with the plot command. So you can see first one, I have figure 1 and figure 2. Figure 2, I didn't set the color map. The first one, the color map was hot. As you may see over here, that the color map was set to hot. Alright, and then I request to set up the color bar. Okay. Oh, thank you, Shannon.
First one.
Whoops, sorry. Oh, okay, I need to turn that off. Okay, the speaker. Right, okay, great. So if the sound is good, then I continue with the confidence. So this works, but this figure 2 I didn't set anything about color map and color bar, so it just showed the default setup. All right. Okay, so here is going to be the output we look up for. I think I can move back to the main. Okay. Alright, welcome those of you who just joined. I just start a little bit, and I just show that the command field is gonna need four data. The data structure just need 4 at least in order to construct the polygon of 3 nodes. So the last node has to be like the first node. Just that. Okay. Right, so I come back here. Now, let's think about the data structure. I haven't finished my cup of coffee yet. So, second coffee of the day. And 1 cup of milk. That's for lunch. We should be well prepared for the difficult time, as the city might be it is getting harder and harder to live these days. So eat less, people. Don't eat too much. Oh, okay. So basically you just need coffee to live. Come back here. I will need to set things up this way. So let me see. Okay, we gonna define the figure to okay. Then I think I gonna need to set up the space such that the plot area will be open or not. So I'm gonna put it has to be below this. So if PEXX plot epsilon is equal to 1, then well, I think this is what figure make it figure 11, yeah, equals to figure 11. Is that going to work that way? I try something. Figure, I think I don't need to put them in sequence, right? Yeah, just do things on your scratch pad. If you're not so sure about anything, just try it out. Okay, figure 11, yeah, it's gonna work this way. Not gonna cause you a problem. Now, the figure 11 is open, then else if PEYY is equal to 1, figure 12 is coming in, figure and 12. One bad thing about doing the live is that if I take too much coffee and then I by chance have a heart attack, nobody is gonna rescue me. I think maybe some of our students are in the room, which is not so far from my room, so I can come knock the door, or yeah, just try to open the door. else if PSXX equal to 1, figure 14 is equal to figure 14. And what else if PSYY is equal to what figure 15. Well, so today you had a lot of live classroom because you just finished up the earthquake engineering just probably a few minutes, and then you come back to this thing here. But you can watch it later. It does not need to be just right now. I copied the video file to process back home, so don't worry, you're gonna get the high resolutions within 1 or 2 days. But I just think that I should talk about this field command, and once I talk about it, I think we can just finish up this code. Hopefully we not bump up with the bug, too bad one, I guess, hopefully. Okay, so yeah, to turn on the plot, and then this is just for each of them. Okay, that looks like a crazy stupid lines, but okay, fine. I don't like to prepare these options because I know that ultimately I'm not using the code. I just make it for fun. Okay, so this is the option to open the new figure for each plot, and then on the next part here, that holds on. Does it need to be like specific for each of them? I think it has to. So hold on. Maybe we should try over here, and then I come back to let's say I make the B, copy, and I just want to explore. Well, guys, you know, I write the program, but I never really sort of keep all of this information in my brain for longer than a few weeks. So basically, it could be a few days. So in a few days, I just forgot the syntax, and that is a very bad thing, because once I forgot, then I got to come back and see, okay, how the syntax really works and how this and that works in the program. So bear with me. I need to do something on the scratchpad, and this class, as you know, the style, can I just call figure 2 like this? We'll see. Yeah, so I always forget. If I want to come back to figure 2, can I just do figure 2? Like, okay, probably. And then so there is no need to ask anybody when you want to find something out. You just check with yourself. Okay, see, let's see if it come back to figure 2. Okay, okie dokie, what the hell is this? Oh, and another thing, my student knows my language is brutal, so what the hell is this thing? Is very simple thing we have in the class. And what the hell is this thing? What is it? I just made the figure B. Why is it on top? Oh, okay, stupid thing. Right, it was supposed to be 2. Okay. 2, 0, 1. And then 5 can also be 7, and 4.5. Okay, and the last one is gonna be 2. Okay, yeah, just silly things. Let's try again. What? Why? Why is it 0, 2 to 0? Okay, I'll just need to specify the range, right? So x limit what? 0 to 10. X is equal. We'll see. What is includes the whole plot. I hope it doesn't just, well, wow. 0 to 2. Let's take a look at the figure 2. Okay, alright, I see. We need to do the hold on. Okay. If I hold on, we'll see another time. Okay. Did we close out first? Okay, and then re-execute. Oh no. Okay, that looks good. So I try to plot, but let's see. The B3 is actually the same thing. Color map. Cool. Is that a cool? Yeah, that's a cool. Color bar is on. Why is it giving the different color? That is the mist still. Let's see. Well. Did I multiply or something? Oh yeah, this is 3 multiplied by okay. So supposedly if I change this, then I'm not going to see the different color, and then I just move this out aside in the x direction. So the max is 5, then this is gonna be 5, this is gonna be 10, so there will be no overlapping, and this is gonna be 7.5. Okay, save it. It's just some lunch exercise, guys. I told you. Why is it still there? The number 2. Why the 2 one corner is still there? Let's see. Well, stupid. Stupid. Okay, now it's gotta be smart. There you go. Yeah, we get identical. We get the identical color plots for these two, but just the height different a little bit because we intentionally made it. 1.5 is scaling there. Okay. Right. I think we are good now. In order to use this fill command over here, then we come back to the FEM. And this is something you should do. I mean, not only just doing this coding for this class, but when you do the coding for any purpose, any applications, and you want to make sure that you do all the things right, you just do it in a little small program. And once it works, then you can extend this into the bigger program, because if you just embed it into the big program, then you're gonna find a disaster when you want to find a bug, or if it doesn't get to work in the way that you wish. Right, so we're gonna set the hold on for all of this such that it will not erase the previous the plot in the previous step. Okay, now this is all the administrative issue. We come down to here where we start the color plotting. For those who are not in this course, I mean, whoever just by chance stop by. So please understand that this is a style of this course that we're gonna do things in a very raw format like this. So I just write the code and I just do it together with the audience or with the students. So I have no piece of paper with the code written already just on my the side, right? So we are doing some sort of trial and error basis. Not that bad, but okay. We expect to see bugs and errors in this development, and this is what the normal human being will do, right? If you want to see a guy who does not leave any bugs or any error in the coding, that will be like just the movie production. That's not the reality, and I don't want any of you to have some impression like that. Okay, we are human beings. Okay, yeah, come back. So for I and ELE, we get the temp, which is okay. This is a temporary. Okay, this is not good. It should be E type plus 1. We must have the last node to close down the polygon. Okay, and then J, this is to transfer the information of the coordinates into the. So I think this ought to be just 2. All right, this let me change the name. Okay, I'm so sorry, but I changed my mind. TMXY. So this includes only the XY coordinates. The magnitude of stress and strain will be stored in the different variable name. Okay, so it will not be like that. If it is alright, then TEXX is equal to what? Zeros? Element type plus 1, comma 1. That's it. Copy it. One thing in coding in front of you is that I cannot just sit back and relax for a while to just get my brains to cool down, because I don't want you to keep waiting for me, so I've got to just continue and do the non-stop coding, which is bad for me. Sometimes I need some short break, because now I can many times I can fry the eggs on my head, and put a raw eggs on my head and you get a fried egg, because the brain gets heats up doing a lot of coding. Alright, okay, so TX will be allocated, and if it is not necessary, then it will not be allocated, so it will not waste your space in the RAM. Okay, so we come down here, we have all the coordinate transferred into temporary X and Y coordinates, and then N4. Basically, TMXY of the E type plus 1 comma colon is going to be equal to TMXY is 1 comma colon. It has to be the same. It should be identical to the first node. So it close down the close down the polygon. Okay. That's one thing. The second thing is that we have to transfer all the stress, strain, which are is that a good idea to put too many variable names? Just do it. This is just a good thing to do during lunchtime, so you just watch and see my pain. Fine, you don't have to do it by yourself. TEXX for that stand for the epsilon, T epsilon YY and T gamma XY, and then temporary stress XX, temporary stress YY, and temporary tau XY. One bad thing about online teaching is that I can teach anytime I want, and that is bad for you because, well, if I by chance get to like energetic, so I just grab the encoder and stream what I want to teach. I'll be out of job soon because I teach most all the things I have probably, so it'll be on YouTube. I'll be useless. Anyway, TEXX, okay, is got to be taken from the node J. No. From okay, J3. No, not 3. 1. This is the 1 column array. Okay. And then this is from we need to solve right, we need to solve deform. No, okay, so we solve, and then we can get NSTN and NSTS. Okay, so these are all taken from NSTN1. This is NSTN2, this is NSTN3, and this one is NSTS1, NSTS2, and NSTS3. That's it. And we know that all of these NSTN or NSTS, they have their dimensions are identical, n node by 1. It is the column vector. And in order to get the right location, we need to use the n map of what? Element I and the j node, right? That's it, comma 1. That's it, that's all. So the dimension of this is equal to number of nodes in vertical direction, and we need to go pick up the stress at the right node in order to fill in for one element, right? Since we are going to do the plot in the in the z direction, we're gonna do the magnitude plot. I'll show you. It's gonna look like this. So this is your element. This could be the three-dimensional picture. Put this there and put this there. This is just to visualize you what I want to do here. because many of you might be confusing, might be like questioning what the hell is going on here. And the only hell which is going on here right now is just that I'm trying to plot this magnitude. The magnitude now, it is like the quantities of any quantities. It could be stress, strain, but okay. So for example, this is the Q4 element that we finish the calculation. We have the magnitude of strain. Let's assume that it is the epsilon x at this node, this node, this node, this node. So we have different values. We need to plot. Well, one way to plot, you can do the 3D plot like this. So you're gonna see the picture pretty much like this, as a connection between the dots. That is okay. So you're gonna see the profile or the plane, which is constructed from these 4 sides. In between the program, well, you're gonna have the interpolation from these 4. But the point is that it is difficult for us to see, okay, in the 3D like this. This is just one single element. If we have like several thousand elements in your plane problem, it is super difficult to see this. So let's say we will look at this picture from the plane view. So from the plan view, just no feel. Right, so from the plan view, you will see the nodes. But now you cannot see that those lines that constitute the profile of the distribution of strain. This profile cannot be shown when you look from the bird eye view. So we got to change the strategy from the line like this that shows the magnitude associated at each location into the color. Or you can opt for the contour plot if you wish. MATLAB, Octave, they are capable of showing both the contour or the color plot. The color plot will be given by the fill command. The contour plot, well, you go look up for yourself. I don't remember. If I want to do it, I just go up and look up for it. Okay? So I think you get what we are doing right now. We are trying to present or visualize the magnitude of quantities, whichever quantities, okay, but it is a quantity at the point on the 2D plane using the color plot. Okay, hope we are on the same page. Hope you all understand what I'm trying to do. Okay, so now I transfer the strain and stress into the temporary array, which is used for the plot for the individual element. And then I got to, I hate so many if like this. This looks stupid to me, but oh gosh. And then we store, this is TORE, store the values of closing closing node, which is only just one node. Okay, so TMXX, why is it? Oh, okay, it has to be below. Sorry. So TMXX gonna come later. Yeah, we paste it. You know, when I was in my undergrad level, Actually, at that time, I can opt for all the departments. So from computer engineering, that requires highest score, highest GPA in the first year, to civil engineering. At that time, I thought to myself that I do not want to be in front of computer coding like this. I want a life outdoor. Well, maybe going out, see building structures, constructions, etc. And then I end up here coding like a geek. And my computer engineers pals are not doing this. So this is quite funny. Anyway, I'm not that good, okay, in coding as much as my pals can do. Okay, so we are going to store values of the closing nodes for this, and the closing node coordinates gonna be the E type plus 1, right? And just gonna copy this to all. This is laborious. Well, fine. I know it is laborious, but if we have this all well constructed, and we have the YouTube here, so next year I'm not going to talk about this laborious thing for another time. And this is going to be the TEXX 1, 1. This is identical to the first node, so we don't need to go look up to NST, and that's gonna waste the time. TEYY 1 is in there, and then T gamma XY is filled in 1, 1. Temporary stress XX 1, 1. Temporary stress YY 1, 1. At the graduation of my PhD, actually I applied to a finite element software company, Plaxis, if you know. It is very well known for geotechnical analysis, finite element analysis. But I got acceptance already, but I don't want to move to the Netherlands because I have enough time in the US already away from home, so I want to come back home. So spending many years later in the Netherlands might not be, it was not a good idea for me at that time. But if I get that, if I agree to move to the Netherlands, then I will be doing all of this like daily basis. Right? So we wrap this up. We get the last node, okay, copied from the first node information. There it is. And then we are going to plot, right? So the plot should be inside the same if, because that's going to be conditional. N4 will be out there. Okay, so now we have the temp XY well established. We have the temporary strain well established. Right now we are able to do the fill command. The fill command will use the TMXY. How about the first index? First index gotta be colon because it's gonna be for all rows, and the column number 1 is the X, right? Next, TMXY, comma 2. Okay, and the last thing is gonna be TEXX whatever, but I just need this frame to be copied. Oh, not just this. I'm gonna need to say that I'm dealing with figure 2 right now, or whatever figure. So let's see what figure. 11 to 16. Okay, so well, what, just go figure like this. Okay, figure 11. If I don't want to delete it every time, then I just copy it this way and paste it and paste it, paste and paste and paste. Alright. It's like I'm trying to develop a finite element software for sale. 14, 15, and number 16. Okay, so the code knows that we are talking about this particular figure, and then it's gonna fill into the right figure. So here we need TEXX, comma 1. TEXX has only just one column, and here TEYY 1, not 1, column 1. Okay, so I should just copy this. Oops. Copy, Control C. And here TGXY, comma, well, okay, alright, TSXX and paste, TSYY and paste, and TTXY and paste. Okay, so the fill command is going to work in each individual plot. If we disable the plot, then it's not going to pop up, to show up. Okay, so actually we shouldn't just waste our resource, so I just cut it from here. No, undo first. Okay, I leave the K inverses here and I put here, so in the future I will not look at my code and say that what I did at that time, that looks stupid. To be used below. Do not delete this. Okay, right. And there it is. We come down over here. So if I don't want to plot, then there's no point, right? There's no point to inverse. But if I want to plot, then just inverse. Well, we should be stingy with the resource for FEM. Every millisecond counts. So the computer time every millisecond, and if you think about the scale of the simulation, which is huge, if you have a million degree of freedom problem, and if it is the nonlinear time history analysis that is going to repeat for several thousand or several 100,000 times to finish up your analysis, milliseconds could turn out to be hours or days if it adds up. So some silly thing shouldn't be left in your code, but okay, we are not the computer engineer, so we are not trying to streamline the code to that level, but some easy level that we can help the computer, we should. Okay, so we perform the inversion in order to find the NSTN, right? N strain, N stress. We perform that when it is necessary. Or the F's, okay, restore, and we can just use them later. Okay, let me check the dimension a little bit. So F0. Oh, wow. Yeah, you find this. We find this. This is a stupid mistake we had in the morning. Then, if we execute the program, then we end up with a problem. So the cases is going to be just n node by n node. We don't have 2 times, right? Because this is just one unknown at a node. Good that I see this. I have some bad feeling about it. So, and these 2 guys, they are not useful anymore. So I kill them out. So F6. Okay, this is consistent. This is consistent now. K inverse. Alright. And come down to here. K inverse is NDE by NNDE. F6 is NNDE. So this turns out to be NNDE. Number of this. Okay, NNDE. Okay. Bug is everywhere. But if we are lucky enough, then it has to be super lucky to leave no problem on the back, or super careful, in other words. If not lucky, then super careful. Okay. Alright. The dimension seems to be in line. E this 2 times E type. Element displacement. Okay, displacement has to be 2 times. Hey, what? Hey, and what is going on here? Why is it a space? Let me check. Okay, the dimension for BMAT, it's okay. The E this is okay. The dimension has to be 2 times. Okay. Element XY, fine. F elite. Okay, fine. And numerical integration. Okay. And shape has just okay. Well, we're gonna see. We're gonna end up with the bug at the end, of course. And then I'm gonna go spend some time find bug for you. I will not keep you here if the bug is like taking me more than 5 minutes to find. Right, but let's look through a little bit before we bump up into the jackpot, because I really hate to see that jackpot at the end. Okay, so look at all of these. Oops. And shape. Well, E strain. Alright, element strain comes out. Element stress comes out. Stress and strain comes out. And then at a given point, okay, at least we set 0 to all of this. So, okay, we set 0 to all of this, and FELE. Okay, we construct the force vector. Okay, so we have as many number of rows as the number of nodes contained in one element. We have 1, 2, 3, 4, 5, 6. KELE is the E type by E type. Alright, looks good. And then shape function times the strain 1, 2, 3, 1, 2, 3, Jacobian of transformation, weight number weight number J, and weight number K. Okay, looks good. KELE will be accumulated N shape and N shape transpose Jacobian weight. Alright, dummy just keep counting on, so dummy will be reset up there to 1, and then okay, keep using it. Okay, and if sys is plugged in, k sys is plugged in, if sys we have n NDE by 1, so we take the node from nmap, we didn't multiply by 2, which makes sense. So above we had previously multiplied by 2, that was supposed to be wrong, and we fixed it already. Then we prepare the k inverse over here as the k sys, and then take the inversion, we keep it there for a while, we plot the deformed shape. This part works already. We come to the plotting, let's say the strain and stress plotting conditions. Let's say option. It is not a condition. So we have an option to plot, or if you don't want to plot, then you disable the plot. It just takes your time, and actually this could be added. So if you want principal stress, principal strain, then you compute it further from xy and torque xy. You go back to Mohr circle and read a little bit, you'll be able to find all of this out. Okay, set the option, I turn all on for now, and then I allocate. So if it is on, then I find the nodal point strain number 1, nodal point strain 2, 3, stress 1, 2, 3. I also allocate the temporary xx, yy, alright, yeah. And then we come to the loop for the element for color plotting using the fill command. So for I equals to 1 to element number, we're gonna do one at a time. We give the temporary xy, so this is a good reset, so we're gonna get all zeros in here. Well, anyway, and then we set up, okay, j, so this is go from node 1 to the last one, so j equals to 1 to 4 or to 8 or to 9. xy coordinate, okay, it was taken from nmap, so we take the nmap element I and node number j of that given element. Okay, we get a node number and we take the x coordinate, which is the index 1, y coordinate is a column number 2, so indexed by 2. In fact, this is not efficient, so I just replace the code by this here. So we save one line, right? Yeah. And then next, so this is inside the for. So I put the conditions for if for all. Actually, we can do the else if, right? It does not need to be an if. No. It should be an if. Okay, and then start a new if, because if it is the else if here, and if it satisfies this, then it's not going to do the rest of this thing. Okay, so it should be the separate if and if. Okay, separate them. Okay, so we collect the stress for or strain for each component we want, as we predefine at the beginning, and take the information from this big array into the little array which is pre-allocated over here. The size of this array is e type plus 1. Okay, we come down to here, and then we copy the first row. We copy the first row information to the last row because we need to close the polygon to the first node. And then we store the value to the closing node. So if we have the if we turn on any of them, then this operation is gonna take place. So the copying of the first node information to the last row of the array is gonna happen, and then we execute the plot. So we call each figure separately. So if it's on, then figure 11, and then filled by TMXY is the coordinate for the XY coordinates, and this is the magnitude of the strain XXYY, shear gamma XY, stress XX, stress YY, and S stands for sigma, and then tau XY. This looks good, but it always works like this. It always looks good, and then that bug happen. So let's call the function. Okay, this is the $1 million moment to see if this code work properly or not. We have no time to come back to visit this thing. Well, but this is easy thing. All right, can I get the drum? Main update. It's gonna take a while. Oh, long calculations. Oh, bug happened already. Yeah, bug happened already. 290. If PEYY is that PEYY, else if. Okay, guys, that's what I said over there. It was supposed to be this, and if, right? You see that PEXX, once this argument is correct, once the PEXX is equal to 1, then it does not call the PEYY and the second, the third up to the sixth one. So we need to do not chain them together. We need to unchange them. Alright, so it turns out to be like this. Yeah, this is quite interesting. Why it doesn't see, why the code doesn't see that line, and it is because of the way we chain things together. So we will need to clean this sort of structure out if we find more than one place like this. But we cleaned it out previously already for one place. Okay, so we have a separate if, then if this, then okay, and if this is correct, then okay, and on and on and on, and then we have if and if and if. Okay, so this works. This is good, this is good. Okay, and if and if and if. Okay, save it and call it one more time. There you go. What? Stop already? Okay. Let me. I think we get it. Yeah. Stress X, stress Y. Well, beautiful. Okay, so we don't have the serious bug. We found it. We make it, but we just need to do a little things with the code. So figure. There are better ways to set the format of the figure, but again, I don't keep that in my brain. So the GCA and command like that, very efficient. Close CLOSC, close all. Yeah, first, and we add. I don't put the 11 here. I put 1, and then axis equal. Okay, we need the equal axis What we plot over here is the stress on the stress or strain on the undeformed configuration. Okay. Color map. I think we have many and we should choose a color map. I think we're gonna use a jet. Yeah, we have so many choice to select for the color map. So the jet one is a very good one. You can change autumn, winter, spring. Well, that depends. If this doesn't visualize you as good as you wish, then go Google up and look up for color map MATLAB. Then it's gonna be identical to MATLAB. It's too bad. MATLAB made the documentation such that people who use the freeware like Octave can go look up for MATLAB documentation and use it. Okay, so color map is going to be jet. What else? We have equal axis color map jet. These all. Color bar. Yes. And that's it. So let me see. No, it is the if. I gonna have to have this if, but it's a lot of if. Anyway, fine. We just clean it. Format and indent code. Whatever inside, delete first. Delete. Now at the end of this lecture we have a nice software for the analysis of a plane problem. The only bad thing is that it is not that fast. It is in Octave. MATLAB does better job. Well, if you want to put this in MATLAB, you just modify your code a little bit. Then format plots. So modify a little bit, change if to n4 to n. This sort of syntax, just indent. Okay, and 11, 12, 13, 14, 15, 16. There it is. Save it and run it. Oops, sorry. Yeah, we'll see. Yeah, this is stress. This is Y stress. So for this problem, as we apply stress at the mid node, at the mid of the span, we see the vertical stress like this, and stress in the x direction looks like this. Does it make any sense to you? You can use the sigma equals to mc over I in order to find the corresponding stress at a point. And the color map on the side tells us the stress level. Now strain, so it is a shear strain. As you apply force over here, so shear strain is one sign over here and the negative sign over there. And yeah, vertical strain looks like this. Horizontal strain epsilon xx looks like this. deformed shape looks just like this. Okay, so we have a beautiful code over here right now. How much time did I use? This is 1 hour already. Well, we can continue. So this is a format plot. I get it all done. I just play a little bit further. So save it. Number 8, number 9, like this. Okay. This code works for Q8 and Q9 also. So don't worry. I just try the 4 nodes. For Q8 and for Q9, we're gonna have some problem over here. Let's see. It is not the bug. It is just headed. So when we migrate the data from the nodal point, we're gonna switch around for a Q8 and Q9. That you, if you remember. So almost 400 line mil. This is nothing. We talk about like millions line of code for those who do regular basis coding. This is nothing for 400 lines code. It is so simple. But the point is that if we execute this code in Q8 and Q9, we're gonna end up with an ugly plot because we don't switch around the nodes. So well, I hate to keep everything in here. It is just a long code, but well, better not calling this plot from elsewhere. So okay, we are going to put the if in order to just take good care of the node sequencing, because the Q8 and Q9 are not like Q4, right? So this works for Q4 because Q4 follow the order 1, 2, 3, 4. But for Q8 and Q9, you got to plot like 1, 5, 2, 6, 3, 7, 4, 8, and come back to 1. That's the problem for Q8. Well, which is bearable, right? So let me what? So this one does not need the special treatment, right? For Q8, Q9. This is going to, well, yeah, it doesn't need any special treatment, but inside the color plotting over here, we need the special treatment, which this whole thing has to be nested inside the if. So if this is Q4 is 4, the Q8 and Q9 they could be in the same. They will live together for Q8 and Q9 because we are not going to plot the 9 node. Okay, so done for Q4. Color plotting for Q4. Oops, what? Then I make the Q8 and Q9. So copy the whole thing, paste. That's it for Q8 and Q9. There it is. Okay. So if element type is equal to let's make it this way. is greater than 4. I'm not sure if it is usable or not, so I should close all first, and a equals to 1. A greater than 1, is it usable? Answer is 0. Okay, then this works. So if element type is not 4, if it is the Q8 and Q9, then we're gonna use this. And NELE, sorry, I shouldn't erase this. NELE, the element type plus 1, let's make it explicitly to 9, so to avoid any calculation. Then we loop over the J to the element type. Not necessary, we need just the 8 point, so we don't go up for the 9th node. And then come down, we don't have anything, right, with the 8 and 9 thing. Over here, the node number 9 is going to be equal to number 1, and this is number 9. Okay, number 9 is equal to number 1. I hate to do this. It's just too many. Format plot doesn't need. So this format plot can be outside. Actually, we can cut it and then put them separately and make these format plots make it sorry. So standalone format plot outside. Format plots. There it is. Okay, it locates outside now, and for NELE, hey, it should be. It's correct. It was inside the if, so we don't need. As long as the Q4 Q8, the format plot is going to be identical. We are not doing anything different. So I save some space. Format plot, just take it out. Over here. Okay, recording is still going on. Hopefully everything works properly, and then we can upload another video. This is 19_2 class, second episode of class 19. Back in here, and if it is greater than 4, okay, so the 4 is the 4 to element. At the end over here, we are, not end over here, we need to switch around. So as we need to switch around, I'm gonna have to 1 to 8 was taken in there already, and the 9 node okay, let's do it this way. We just need 8 for here, and then T M X Y is equal to 0. 9,2. Okay. I had to reassign those too many variables. The code doesn't look smart. That's what I hate. Okay. Then ttmxy 1, colon is equal to ttxy row number 1 and both column. So we foresee the disaster and we are fixing it now. The number 2, when we plot, it should be taken from coordinate number 5. The number 3 will be taken from coordinate number 2. The number 4 will be taken from 6. Number 5 will 6, 7, 8. Basically, we're gonna need the 9 already also. So, okay, 1, 5, 2, 6, and then 3, 7, 4, 8, right? And the last one is the 9 node is taken from the first one. So the coordinate x and y of each individual element is now following the location. It is not following the shape function. If you follow the shape function, you're gonna get the very, very messy plot. So I have to shuffle it around such that 1, 2, 3, 4, 5, 6, 7, 8 turns out to be 1, 5, 2, 6, 3, 7, 4, 8, and come back to 1. For a Q9, we are not going to plot the node number 9 because it is just in the center of the polygon, and that's gonna be messy because the polygon is it is a closed loop polygon, and we just need the line on the boundaries. And now we are going to put another t, right? So the procedures over here is going to be replaced. So here I'll copy and I will change the name of the variable. I'm not sure when you watch live if the quality of the resolution of the video is as good as in YouTube or not, but from my view, from my PC, I see the screen which is not so clear. So I'm not sure if it works that way or not. But later on when I upload it onto the YouTube, it is just crystal clear. Okay, so what t temp exx, and that's a 9,1. Or the picture quality is just bad at my PC only, or bad at your PC as well. Fine. Okay, so 1, 1. Exx has to replace, right? and T it has to be what T TEXX, right? Like this, very pure CTXX. Yeah, this is a laborious part. I don't see the video moving. Okay. Okay. I think this looks good now. So the temp XEXX was initialized to be 9,1, and then it transferred the TEXX into this, and okay. So this is lovely right now. I then clean this up and paste it like this. So as I paste it here, TEYY, so copy. Once we finish this, I don't think I will execute the Q8, Q9 code. It's gonna take so much time. But I can just upload this and you can play with it. Paste and paste. Long code, and this one has to be another T. Paste. Right. Yeah. Okay. And continue. So EYY is done. It's taken from TEYY, then paste it. So sorry. Gamma, right? Gamma XY. Copy, and this will be double T. So I paste Gamma XY. If you don't want to watch, well, just leave, because this procedure is just time consuming. So if you go out to get something to eat or do something which is better, then feel free. You can fast forward when you watch this procedure on YouTube, because it definitely just take your time. Okay, done, and a few more. So 3 more for stresses. I just drop it first, and there it is. The another T. We need SXX. We need SXX, so I drop in SXX. Oh no, nah. SXX. SXX. Let me see, in the YouTube, in the video, I can speed up the procedure over here, so it is like a fast forwarding, and then You will not need to spend the long airtime over there. T, another T, and the triple T over here. So SXX is done, so SYY. Actually, yeah, replace, can I just control phi? Yeah, stupid. So phi what? Phi GXY replace with SYY. Okay, phi next and replace. Oh, smarter. Work stupid takes more time. Work smart takes much less time. Alright, the last one, replace. Bang. Okay. And then, why? Too bad. I just found, just come up with the thought at this point. T, X, Y. So, replace. Okay, you don't want to go there to change it. Oh boy. Okay, so we have all of this fixed. Then for Q8 and Q9 it's going to work now because we switch around the location. So this is appropriate for our plot. Alright, we'll see what else do we need. If you want to draw the deformed shape, if you want to plot the stress on the deformed shape, that is also possible. You just use the coordinate along with the exaggeration factor with the displacement multiplied to the exaggeration factor, and then you add them up to the xy coordinates. So you get the update coordinates, and then you can plot stress on the deformed shape. Okay, so the picture is going to be like the mesh will be deformed and the stress will be on that deformed configuration. So the only thing we have so far that is not up to not fully automatic is the quite a long code to scroll up and down. This part here, I think I'm gonna fix this. We're gonna fix this part. Boundary condition is good already. Displacement is okay. This part here, if we use the better solver, like in MATLAB, we might be able to use some sparse solver, Super LU or so, that could be integrated to MATLAB code, and that makes the code run much faster. But again, you are not selling this code, so if it just works, you're fine. That's another detail that you got to spend quite some time to figure out. So force will be applied systematically. That could be in a separate video. It is just an administrative issue. It is nothing so fancy about the finite element concept in order to apply force systematically. And this part here will separate the code into two parts. So the first part is the pre-processing. The pre-processing, we give the geometry. We will save the mesh into the text file, and from that text file we can save either everything, the mesh, xy coordinates, the end map, right? That's the mesh information. You can input the boundary conditions. Yeah. So you can say that where is the support. You can input the apply external force. That's gonna be in the text file, and we save the text file, and every time we execute, we're gonna read the text file and run the main engine of finite element. So the solver and the post-processing is in this routine. So we're gonna break it down that way. But first of all, this part shall be changed into the input, the read input from the text file.